Hi everyone, today I'm going to talk about multi-agent pathfinding with mutex propagation. Multi-agent pathfinding, or MAPAT, is a widely seen problem in many real-world applications like multi-drone planning system, automatic warehouse, or game AI. In this work, we show how to use mutex propagation to improve conflict-based search, or CBS, which is a state-of-the-art MAPAT algorithm. To begin with, we show a small MAPAT example with two agents. The blue agent is required to move from C1 to B5, and the orange agent is required to move from D2 to A4. At each time step, agent can either move to a neighboring location or wait at its current location. The cost of an agent is defined as the time step of very beginning to when it terminates at its goal location. Here, we want to minimize the sum of cost of all agents. So one of the optimal solutions of this instance look like this. You can see that the blue agent waits at its start location for one time step. That is because if both agents move to their goal location without waiting, they must collide somewhere in the map. Let's see how CBS will solve this instance. In the Luna of CBS, it will plan the shortest path for each agent individually and then detect whether there is a collision. Here, we find the collision at location C4 at timestamp 3. To resolve this collision, CBS branch into two nodes. In one node, it adds a constraint to the blue agent to prevent it from using C4 at timestamp 3. In the other channel, it do the same thing to the orange agent. And then CBS expand left channel in the same and resolve the collision in the same fashion as what we showed before. Now, if we considering this rectangular region between the start location and the goal location of agents, let's denote h as the height of this rectangular area and w as the width of this rectangular area. It has been shown that CBS has to expand at least 2 to the power of minimum WH nodes, which is nowhere ideal because it means that with a larger rectangle, the number of node expansion also goes exponentially large. So the example we just shown is also known as cardinal rectangle conflict. So what is a cardinal conflict? Two agents have a cardinal conflict if and only if all shortest paths for the two agents collide. Here, we show another three examples of cardinal conflict. As we have already seen, applying constraint one at a time can be very inefficient in resolving cardinal conflict. In these three examples, we also annotate one or two geometric parameters of the map, and we will see that with this parameter increase, the number of node expansion by CBS will also go exponentially large. Existing work make use of human design rule and can only resolve case A and case B. In this work, we use mutex propagation to automatically identify and resolve all cardinal conflicts, give us an exponential reduction in the size of CBS search tree sometimes. Mutex is short for mutual exclusion. Mutex propagation has been used on planning graph to approximate set of reachable states. Here, we use mutex propagation to identify the possible joint states of two agents. First, we need to represent all shortest passes of each agent into a compact data structure called multi-value decision diagram, or MDD. Here, we have two MDD for the blue agent and the orange agent respectively. MDD is a leveled directed graph with one star MDD node and one goal MDD node. Every passes in the MDD from the star MDD node to the goal MDD node corresponds to a shortest path of the agent and vice versa. Mutex is defined as two MDD nodes L1T in the MDD for the first agent and L2T in the MDD for the second agent are mutex if and only if all passes for the first agent to L1 at time t and the second agent to L2 at time t collide. To identify all mutex between these two MDDs, first we need to find the initial mutex, which corresponds to collision between the two agents. In this example, We have 6 locations in the map where the shortest passes of agent might collide, which give us 6 initial mutex, which are those blue arc connecting MDD nodes of the same level. Then we need to propagate our mutex. 2 MDD nodes are propagating mutex if all pair of their parent MDD nodes are mutex. For example, here, because C4 is mutex with both orange B3 and orange A2, so that we can propagate our mutex to this blue C5 and orange A3. After we find all the mutex, we can answer the question that whether we have a cardinal conflict. If we look into the goal node of these 2 MDD, we can see they are mutex, which means there does not exist a pair of collision-free passes for both agents to reach their goal location at time step 5. By definition, it means they have a cardinal conflict. Then we need to we want to generate a constraint to resolve this cardinal conflict. First, we need to pick 2 subsets of MDD node from each MDD, such that this MDD node is mutex with all MDD nodes of the other MDD at the same level. For example, here we will pick this B4 because B4 is mutex with all MDD nodes in the blue MDD of the same level. In CBS, in one of the channels, we will transform these 4 blue MDD nodes into 4 constraints at corresponding location at corresponding time step for the blue agent. And in the other CBS node, we will do the same thing for the orange agent. We can see that in both CBS nodes, we find collision-free paths. In the paper, we prove that conflict-based search with mutex propagation identify all cardinal conflicts and is complete and optimal. Here, we show our experimental result comparing 2 algorithms. The blue algorithm CBSHO is from this 2019 paper. It's CBS with heuristic guidance and rectangle reasoning. Rectangle reasoning is a specific strategy to handle rectangle conflict. And the orange algorithm, CBSH-mu, is our proposed algorithm, which is CBS with heuristic guidance and mutex propagation. You can see that, except in the first example, with the size of rectangle increase, both algorithms are able to solve the instance with only 1 node expansion. In other 3 examples, as the geometric parameter increase, the number of node expansion by CBSHO goes large very quickly, but CBSH-mu is always able to solve the instance with a small amount of node expansion. Here, we show our experimental result on 4 different types of maps from MAPAC benchmark. The 4 pictures above show the percentage of solved instances by these 2 solvers within the time limit as 5 minutes and with different numbers of agents given. The 3rd picture below shows the average runtime, where average runtime among those instances solved by both agents. You can see that except in empty map, where CBSH-mu only has marginal improvement in terms of success rate. In other 3 types of map, we have seen significant improvement regarding success rate and average runtime. In conclusion, cardinal conflict can lead to very large number of node expansion in CBS. Existing work relies on human design rule to handle specific type of cardinal conflict. But mutex propagation gives us a powerful tool to automatically identify all cardinal conflicts and infer applicable constraints. Our experimental result also shows significant improvement regarding success rate and runtime. This is my talk for today. Thank you.